We learned yesterday that an object that moves through the air under the influence of just gravity, a projectile, follows a parabolic path. Now that parabola has two components to it, an x component and a y component. The horizontal or the x component of the velocity doesn't change. So the velocity right here is the same as the velocity here and here and here and here and everywhere else. The x component doesn't change. It's constant velocity, and therefore we could describe it with that very first equation that we learned this year, v is equal to delta d over delta t. The y component, however, has a force acting on it. Gravity pulls down on it. So the y component of the velocity might be initially this value, but then as it goes up into the air and slows down under the influence of gravity, becomes this value, and then becomes this value. And at the peak of the parabola, the maximum height of this projectile, it actually stops vertically. Horizontally, it keeps going at the same speed that it was traveling at before, but vertically, it actually stops. And then as it starts coming back down, it speeds up and speeds up again and speeds up until it hits the ground. Because vertically, it experiences an acceleration, we can describe its motion by any one of our group B equations. The one that tends to work the most often, however, as we saw yesterday, is this one. D is equal to VIT plus 1/2 AT squared. Now, the strategy that we use to solve this problem is almost brute force. We sub in numbers, we get something. If we get time from this equation, all right, sub it into this one. If we solve for time from this equation, all right, sub it into this one. Don't try to solve for something specific, just get something. And if it happens to be what you're looking for, great. If not, then use it to sub into the other equation to solve for what you're looking for. Now, we did one example yesterday. I want to do another example today that's similar to the one we did yesterday, and then we'll have you work on a few questions. This one says, Mr. Dickie accidentally runs horizontally off of a building at a speed of 5 meters per second while trying to escape a mob of adoring fans. Mr. Dickie lands 7.82 meters from the edge of the building, thankfully in a swimming pool. I'm okay, don't worry. Determine the height of the building. Let's draw a picture of this. There's the building, there's me running off the edge of the building, accidentally try to escape this mob of adoring fans. I have a speed here when I run off the edge of the building of 5 meters per second. The path I follow is a parabola. I end up in this swimming pool right here, thankfully, so I'm not hurt. Hot day, so I get to cool off. I land 7.82 meters from the edge of that building. And what we're looking for here is the height of the building. So yesterday's question, we had the height of the building and we were solving for the horizontal displacement. This time it's the other way around. We have the displacement, we're looking for the height of the building. So what do we do first? Just like you'll do on question 1 of your final exam, when you see a question like this, you're going to break it up into x components and y components. The x component, v equals delta d over delta t, because it's constant velocity. We always start off that way. The y component, we can use any one of my group B equations, but this is the one that works the most often, so let's try that one first. D is equal to VIT plus 1/2 AT squared. Now remember the strategy, the brute force strategy. Sub in numbers, get something. We have the horizontal velocity here. I run off the edge of the building horizontally at 5.00 meters per second. So let's sub that in. We also have the horizontal displacement, the x displacement. It's 7.82 meters. We don't know what the time is. That's okay. Let's take the time up by multiplying. Let's take the 5.0 down by dividing. In other words, we just switch places. Delta T becomes 7.82 meters divided by 5.00 meters per second. When we solve for T, it works out to be 1.564 seconds. Good. It's not what we're looking for. That's okay. Let's take that time and sub it into my other equation. We don't know what the vertical displacement is. Yesterday, in the example that we did know what it was. It was the height of the building. That's what we're trying to find today. The vertical initial velocity is, just like yesterday, 0. Look, I'm running off the edge of the building horizontally. How much of that 5 meters per second is vertical, up and down? None. So 0 times time is 0. We can just cross that off. Plus 1/2 of negative 9.81 meters per second squared, the acceleration due to gravity, times the time, 1.564 seconds. We can use that time here because time is a scalar. Let's sub in our numbers. Let's punch it into our calculator. And when we do, we end up getting a displacement of negative 12.0 meters. So the displacement of me vertically, y component, is 12.0 meters. Now, the question technically asks for the height of the building. We just found the displacement of me. If the displacement of me is negative 12, then the height of the building is positive 12. I'd accept either one, though. If you put down negative 12 as an answer on a test, I'd take that. All right, I'd like you to take a look at worksheet number 9. Questions 1 to 4. You've got a little bit of time to work on those in class. Check your answers at the front. And then once you're finished those, we'll do another example that'll allow you to work on questions 5 to 7 on worksheet number 9. But for now, just questions 1 to 4 on worksheet number 9. The next type of projectile motion question that you can see is like example number 21. This one is in your notes package that I gave you at the beginning of the year. This one says a golf ball is hit so that it moves with a velocity of 25 meters per second at an angle of 30 degrees above the horizontal just after it's hit. We want to know how far the golf ball will travel before it hits the ground. And then what's the maximum height of the golf ball? All right, so the diagram is going to look like this. There's the ground. We launch the golf ball at an angle of 30 degrees above the horizontal at a speed of 25 meters per second. Now, this one follows a full parabola versus the last one, which just followed a half a parabola. It's a full parabola. We still describe this with the same two equations. V is equal to delta d over delta t because the horizontal velocity doesn't change. And for the y component, we say d is equal to vit plus 1/2 at squared. We start every projectile motion question exactly the same. This one, however, has something the last one didn't. This one has a funny angle. All of you right now should be thinking 5 words. I don't like funny angles. All right, let's take it off to the side then and get rid of our funny angle. We've got 25 meters per second. We've got 30 degrees. This is my x component, and this is my y component. Let's solve for x, and let's solve for y, just like we did in those displacement problems when we were adding displacements together. Let's say cosine 30 degrees is equal to adjacent over hypotenuse. X is 25 cosine 30, which works out to be 21.6506 meters per second. The y component is the opposite side, so we're going to say sine 30 degrees is equal to opposite over hypotenuse, where the y component is equal to 12.5 meters per second. And we box it off just like we did those other problems, because that's what we do. And then we're going to replace this 25, because remember, it is now dead to us. We're going to replace it with 21.6506 and 12.5. Just like we did those vector addition problems that we were working on the last week and a half. Now let's go to that brute force strategy, sub in numbers, and solve for something, anything. Do we know the horizontal velocity here? If the initial velocity was 25 meters per second, but remember that 25 is dead to us. We're never going to use that number again. Do we know the horizontal component of that? We do. It's 21.6506 meters per second. We don't know the horizontal displacement. We don't know how far the golf ball goes. That's what we want to find. We also don't know the time. All right. That wasn't very helpful to me, but that's okay. It will become helpful to me in a bit. Do we know the vertical displacement? In the last example question we did, the vertical displacement ended up being the height of the building. Negative 12 meters. Well, it ended 12 meters below where it started. This one, this golf ball ends at the same height that it started. It starts at this height, it ends at the same height. So its vertical displacement is 0 meters. Now, in that last example, the initial velocity for the y component was 0 because it was all on the x-axis. This time, the initial y velocity is 12.5. We don't know what delta t is, that's fine. A is neg 9.81. And again, we don't know what delta t is. Now, it's a little tricky to solve for delta t. I'm going to show you a little trick here. The math is a little icky, but we can deal with this. I'm allowed to do essentially whatever I want to this equation, as long as I do it to every term on both sides. So let's divide 0 by t. Let's divide this term by t and this term by t. 0 divided by t is 0. 12.5t divided by t is 12.5. Half of neg 9.81 is neg 4.905. And t squared divided by t is t. Now that's looking a lot simpler now. Let's take the 12.5 over by subtracting. And then let's say 12.5 divided by 4.9 is t, and that value gives me 2.5484 seconds. There we go. How long is the ball in the air for? 2.5484 seconds. Now, let's take that value and sub it into here. 21.6506 equals delta D, the horizontal displacement over the time of 2.5484 seconds. We take the 2.5 up by multiplying, and the horizontal displacement, right, the x component of the displacement is 55 meters. This golf ball travels 55 meters in the air before it hits the ground. That's it. Now, if you were an engineer maybe designing like a golf dome, like a driving range indoors, you might want to know how high the roof needs to be so that the balls don't hit the roof. In other words, what's the maximum height that a golf ball will travel before it starts coming back down? Here's what I want you to do for this, for the maximum height of the ball. I want you to analyze, once again, the y component, because height is a y component. But this time, I want you to try this group B equation. For the maximum height, try VF squared is equal to VI squared plus 2AD. when the ball reaches the maximum height, when it reaches the peak height up here, horizontally, it keeps moving at 21.65 meters per second. But vertically, it has stopped. Remember, it started at 12.5, and then it slows down, slows down, slows down, slows down, reaches the peak height, and stops on the y-axis, and then speeds up as it comes back down. So if we analyze this problem at the peak height, the maximum height of the golf ball, VF will be 0. Now, we're solving for the displacement when VF is 0. So let's rearrange this. We're going to take the VI squared over by subtracting. And then we're going to take the 2A over by dividing. I'm just going to say delta D is equal to negative VI squared over 2A. That's negative. VI is 12.5. Remember, we're talking about VI on the y-axis here because we're analyzing the y component. Divided by 2 times negative because it's the acceleration due to gravity, negative 9.81. You say negative 12 squared. Remember, you're only squaring the 12.5, not the negative 12.5. Divided by 2 times negative 9.81. That gives me a value rounded to 2 digits of 8.0 meters. So this ball would go maximum 8 meters high. When it reaches the peak height, vertically it stops at a height of 8.0 meters. If you were designing this golf dome, then you'd want to make sure that your roof was at least 8.0 meters high. Now what I'd like you to do is have a look at the next part of worksheet number 9. You've looked at questions 1 to 4. I'd like you to take a look at questions 5 to 7 now, please.